something I started talking about last time. If you're going to compare a number of different solutions of dynamics, the way to do this is to take every solution we care about and bring it to our table, and then see how close they're to each other. So one way to think about it, you have a deck of cards with faces of people all looking similar to each other, having mustaches, etc. And now you get some other pictures and you would like to see where you have them in your deck of cards already. So what you do is you take that picture, put it here, you use rotational symmetry to align it, translation symmetry to bring it close to each other, so you use your two-dimensional equivalent symmetry. And then you do something like compare them bit by bit or do something. So you define a notion of distance between photographs. That's called a norm. And you find the picture that's closest in your deck of cards to that thing, and that's facial recognition problem or image recognition problem. So in this process, you're able to process all possible people that you encounter and classify them according to the pictures that you have. And I'm using a word that was used by Jerry Marsden for this. I'll call these pictures that you have, I'll call them templates, because what we think about is that we take a snapshot of, let's say, three-dimensional turbulent flow. So we know at an instant what everything looks like. And we put it in our vocabulary of templates. And then every time when I look at something in turbulence that looks a little bit like it, I compare it to my template. And that means that I'm using a fixed frame rather than using frames that are moving all over the place. What I'm doing is I have dynamics. It's going all over the place. And what I'll do is I will now find the thing, and my pictures tend to be confusing, but I'll find in all of these guys, I'll find a simplest thing to do when you have high dimensional dynamics is to define a hyperplane. So define a hyperplane. That will cut this torus, at least locally. And as I know that this is not only a dynamics, so the things I'm looking at, some curved objects embedded in very high dimension, there is no chance, even though I'll show you in a lecture a little bit later, there is no chance that in this high dimensional dynamics, I can take a plane and cut every group orbit nicely, because they sit on this bagel and I have a knife which is just flat. So this cut, which I'll call a slice, this will be called a slice hyperplane. And I have to be careful about language. This is slice hyperplane. This is not a slice. I'll define a slice in a moment. It's a thing that for some part of the bagel cuts all group orbits. So this is a thing like that. So there are other parts of state space it doesn't cut, but here it's cutting everybody. So at least local is good. Now the global strategy is that when this guy fails me, I put another slice hyperplane, I put another slice hyperplane until I've cut my bagel, until I have every part of the bagel, I've sliced it sideways in such a way that I've cut all the orbits of interest for me. And this is trajectory like that, but it's specified by different conditions. So it's very much like what we did in co-moving. So the co-moving condition was at every point in space, I want the new velocity at that point at time t, that the group tangents, all the group tangents, at that point. I want them to be 0. That's how we got the co-moving frame. Now we'll have a different condition which says there is a hyperplane and I want points to sit in this hyperplane. So a hyperplane always has a normal to define it. And if I have 5 conditions, then hyperplane we have 5 normals you'll have to satisfy for each condition, for each continuous parameter. Here we're just thinking of 1. So this is not going to be no common. And it's defined in the following way. I take a point, x prime, which I call a template. So that says I picked one point in this hyperplane. That's my picture of a man with mustache turned, correct way staring at me and not turned at 60 degrees or 80 degrees. So that's a template. Now the group orbit and now anything that's on a group direction of this point, so I'll make sure that it's orthogonal at the slice. This is group orbit, and that's same point. And I'll call this Tx. And now what I want is I want to look at all the points which are in orthogonal subspace. So if I have one tangent, the hyperplane is defined as a set of all points which are in this hyperplane, slice hyperplane. I'll give it a hat right now. And that's of dimension d, dimension of whole space -1. So if the whole space was million and 1 dimensions, the slice hyperplane is million dimensional. So it doesn't look like much, but turns out it's a great one. So now I have this condition. And now I can write the C case slice. Slice condition is that velocity at any point in the hyperplane dotted is this one fixed point. See, here it was local statement, but this is now global statement. So the hyperplane is divided by one particular point called template at a tangent at that point. Now condition is that the velocity should be in the slice. So this is a slice condition. This is a co-moving condition. And then the same thing works out. I dotted, and for abelian case, it's totally trivial. And I get equations that look very much like these ones. So V is the hat thing that's in the slice, component of the velocity, which is inside and not moving in the transverse to it, but not orthogonal. Here is always orthogonal. Here it just requires no transverse, plus theta dot, the slice at that point, the tangent at that point. But the reconstruction equation is different. Again, Vx dot Tx T prime, because now my condition is this guy, T prime. So this is the component of my velocity, dynamical velocity, any place where I slice in the normal direction to the slice hyperplane. That's what this means. The component, it has to be divided by the tangent at that point. Times the fixed vector which defines the global flux. So they almost look the same, right? There is a, but they have different denominators. What's a big deal? This denominator is just a square of a vector, tangent vector. This tangent vector is always non-vanishing for a general system because every place in the space I have a direction which I move unless I'm in invariant subspace. If I'm in, for example, z-axis of something like Lorentz attractor, the group doesn't change anything. But turbulent dynamics is not there, it's always outside. So this is a nice thing, just positive number, never vanishes, and integrations is totally straightforward. So it's very easy to implement co-moving frame, and our colleagues do this regularly and proudly announce new methods in fluid dynamics, but it's just standard thing. However, this is a product. Let's look a little bit better what's going on in the slice hyperplane. So there's a slice hyperplane. So this is hyperplane, which I'll call M hat. And it has some label because it's defined by this particular template. And all the points in the slice hyperplane by definition, they're sitting in it. And this is of dimension d minus 1, because the whole space was dimensional, and now we have gotten rid of one dimension. This didn't happen here. In this case, the motion in the new variable was in the original space, but this was one dimension less. Intuitively, that's much nicer because it means we have found coordinates in which you have one trivial coordinate every place. And we have d minus 1 physical coordinates, how the things change. So that's good. Dimension is d minus 1. And now what happens is that at some point, let's say this point, we have normality by construction. So t prime at point x prime, m prime. Find the whole thing. This by construction is normal.